Okay, it is now recording. That was weird. Okay. That's whoops. All right. Let's get to talking about one of our last topics of Chem 1A. Today we are talking about inter and intramolecular forces. Let me write that out. Inter slash intra molecular forces. Before we begin, don't forget we do have a wet lab today. If you realize you're not dressed appropriately, now's your time to message someone to carry you anything that you need. Okay. Inter and intramolecular forces. Throughout the course of this semester, we have encountered various states of matter, and we've talked about them to various degrees. We've seen solids. That was mostly in our moles topic. We've seen liquids. That was mostly in our molarity topic. And of course, we've seen gases, which was, of course, in our gases topic. But throughout our time there, we've talked about very physical, quantifiable means of these states of matter. Solids can be weighed with their mass. Liquids can be measured with their volume and their concentration. And gases can be measured via pressure. But today, we're specifically going to be looking at the types of attraction between molecules. So a little bit more qualitative. Let's remind ourselves of the key factors or the key states. I'm going to draw a couple boxes for solid, liquids, and gases. Let's look at the different states of matter. So this should be a little recall for all of us from way back when in Module 1 content, where in the case of a solid, our particles are packed tightly together and are ordered as such. In solids, the molecules vibrate in place. In other words, individual particles will not move left or right. They'll stay in one spot. Of course, the entire solid can move. The analogy I likened it to way back when was something of an ROTC group where individual people are just following the entire crowd, meaning they move as a group. In solids, these particles vibrate in place. Moving on to something like liquids, where in the case of liquids, these particles do have some mobility, but liquids are trapped by the container that they're in. In other words, a bottle of water, the liquid particles in that bottle are trapped within that bottle. So they're just moving around within that bottle. Compare that to gases, which by nature has the freedom to go anywhere. Gases, on the other hand, have much more mobility. If I shake a bottle of water, well, the particles in that bottle are just, well, they're not really moving. They're just stuck within that bottle, just hitting the corners and other particles. But if I were to, for example, spray a can of Febreze, the gas particles would move and envelop the entire room. Of course, the goal is, in the case of a bottle of Febreze, the smell dissipates uniformly. So the idea here is that the motion of the molecules change. In the case of solids, they're pretty much immobile, but they vibrate in place, all the way to gases where they have the most amount of mobility and freedom. Going from solids to gases, we know that the most common way to achieve this is increasing temperature. Ice cube melts at 0 degrees. Liquid water boils at 100 degrees. In other words, if we want to go from an ice cube to steam, we just increase the temperature. Of course, as we know now through both our kinetics topic and our reaction rates topic, increasing temperature also leads to an increase in energy. And it is this energy that accounts for the solids, liquids, and gases mobility. Okay. That at least sets up our discussion so we understand where we're coming from. This has just been mostly a recall. Let's talk now about intramolecular forces. Intramolecular forces are described as the forces between molecules. I'm sorry, not between, within. I apologize for that. Within molecules. A good example of this is the molecule HCl. Now, based on the locations of these atoms on the periodic table, we're able to say, at least with some confidence, the rough size difference between the two. In other words, chlorine has 17 electrons. It's going to be larger than hydrogen. That's just drawn here by just the shape or the scope of these circles. The bond between the two atoms is the intramolecular force. In other words, intramolecular forces are what we've come to expect so far. This includes ionic bonding and covalent bonding. Both forces or types of forces that require two molecules reacting with two atoms reacting with one another. Now, there is something special or unique that arises from these types of forces. We've talked a lot about electrons. And throughout this semester, when we've talked about electrons, we've really kind of treated them as these sort of discrete particles. If I were to draw, for example, a Lewis structure of NH3, we've always sort of treated the electrons as quite literally a pair of electrons, two distinct particles on an atom. But in truth, these electrons actually exist more as a cloud of electrons, where we can say that in a molecule such as HCl, there is a very clear difference in the amount of electrons present. More specifically, there is a difference in the size of the cloud. How do we know that? Well, what exactly does that mean? Well, looking at the periodic table, chlorine is in group 17. It's atom number 17. Hydrogen is atom number 1. So in terms of number of electrons, it should immediately make sense to you why this cloud is bigger. But as a result of this electron cloud disparity, the following phenomena is encountered. We draw an arrow with a line passing right through it like so. And this arrow represents what's known as polarity. The concept of polarity is that it is as a result of an uneven distribution of electron clouds. Of course, HCl is a fantastic example because, as we just talked about, it's very easy to see numerically that chlorine has more electrons than the hydrogen, leading to that uneven distribution. And the term polarity arises from the general logic or the general vernacular of there being a North Pole and a South Pole. Although these North and South poles aren't necessarily one or the other, meaning, based on how we drew it, there's clearly no atom that's north, but rather the idea that there is a clear north and a clear south, such that we can say that the chlorine is slightly negative. I've drawn a really weird looking symbol. This is the Greek letter for delta. This is the lowercase Greek letter for delta. It looks kind of like a squiggly S with a loop at the end. This Greek letter literally means slightly. So when reading this drawing, we are saying that the chlorine is slightly negative. Now, that word slightly is really important. Chlorine is in the molecule. By all intents and purposes, the molecule is overall neutral. But due to the uneven distribution, one end, the north or the south, but one end is slightly negative, such that the other end is slightly positive. This is reflected in the arrow that is drawn. In fact, the reason why we put a line right through the arrow is to visually represent this side is positive or slightly positive. This side is negative / slightly negative. To reuse an analogy you've recognized, the game of tug of war, what we're saying here is that there is no equilibrium. One side is clearly winning, such that one side is slightly negative and the other side is slightly positive. This polarity, again, comes from the uneven distribution of electron clouds. So let's take a look at another example, such as two fluorine atoms. Two identical atoms attached to one another. Do we think there's going to be an uneven distribution? Not in theory, no. I mean, they're the exact same atom. So the clouds should be effectively similar in size. When these such cases arise, this is what's known as a nonpolar molecule, meaning there is no uneven distribution. Of course, there are some cases, carbon monoxide. This is one of those Lewis structure questions I had on the exam, CO. You remember the oxygen is positive and the carbon is negative. There are a few cases where atoms are explicitly labeled as being positive or negatively charged. In this case, what we do see is again that polarity, and we draw the arrow as such. This is, of course, what's known as a polar molecule. And a polar molecule has what's known as a dipole. And when I say dipole, I mean there is a very clear positive, there is a very clear negative end. There is a very clear north pole, there is a very clear south pole. Recognize, of course, that the direction you draw the molecule also affects the arrow. If, for example, I had written the carbon monoxide like so, the arrow would be pointing to the right with that plus sign right under the oxygen, or that strike right under the oxygen. It still tells us the same thing. The presence of the arrow confirms there is a polar molecule, and we can tell from the drawing which side is positive, which side is negative. So take, for example, another molecule, such as OH. Without any sort of context or analysis, if I were to draw the arrow like so, which is correct, you should be able to very immediately visually know which side is slightly positive, which side is slightly negative. I've drawn the arrow for you, so it's just the analysis that the hydrogen is slightly positive and the oxygen is slightly negative. Does this make sense with what we know? Yes, it does. Oxygen has way more electrons than hydrogen. As a result, it's going to be slightly negative. These are cases where we have just two atoms. What about a case like water? Now let's go ahead and we're going to draw the VSEPR geometry for water. We're not going to go through the step-by-step process, but hopefully we're at the point where you should be able to understand how I got here. What about in the situation where we have three molecules? Well, in theory, it shouldn't be that much different. In fact, we can quickly say the dipole moment, or the arrow, is drawn as such, where we can see directionally and visually the hydrogens are slightly positive and the oxygen is slightly negative. Visually, this should make sense because you're like, well, yeah, it makes sense. The oxygen has the lone pairs. Of course, it's going to be slightly negative. But the analysis of such molecules really comes down to that uneven distribution. Yes, Elena. Are you at, so, oxygen beside that is more positive. Oh, you mean in this case right here? That's because we would have calculated formal charges. And remember, formal charges are what tell us this is the charge of the atom in the molecule. So it's not because it's not because we analyzed it and got to this conclusion. It's because we calculated formal charges, right? So let's take another example. Let's do NO3 minus. We're not going to analyze it in terms of which one has more electrons. We're just going to look at the Lewis structure and VSEPR. The VSEPR is as follows. This is just the VSEPR drawing. We should be, in theory, able to draw all of the arrows that represent the uneven sharing. We see, of course, there is an arrow here, an arrow towards the other oxygen, as well as an arrow to the double bond oxygen. And how do we know which side is positive or negative in this case? The formal charges tell us. Intramolecular forces like these are very important, not only because they, number one, help us understand the stability of a molecule, but they also help us understand the interaction of these molecules with one another. This leads to intermolecular forces. Inter and intra. We just did intra, now we're doing inter. Intermolecular forces can be described as an attraction between molecules, so not within anymore, but between. And let's take an example of what that looks like. Going back to one of our earlier examples, HCl, we know, of course, what the arrow, the polarity arrow, is going to look like. We know, of course, in theory, our chlorine is slightly negative and our hydrogen is slightly positive. This is an example of the intramolecular force at play. But how does this help us understand the inter? Well, when we deal with these chemicals, intuitively, you should understand, well, in a liquid or in a solid, it's never just one unit. In fact, you could potentially have another HCl floating around. Why stop there? Let's go even more. Another HCl floating around. These molecules, just as we saw in solid liquids and gases, have some mobility. They're able to move around. So eventually, these three molecules will all meet up. They're all going to meet up eventually. How do they meet up? Well, remember when we said that hydrogen is slightly positive? Don't we know that opposites attract? So what is going to be attracted to the slightly positive hydrogen? The slightly negative chlorine atom. As a result, what we end up with is an intramolecular force between the two molecules. In this case, there is no explicit polarity. It's rather, as a result of the uneven sharing, molecules can be attracted to one another. And guess what will happen once again? Another molecule will come right on in and say, hey, I'm slightly positive or negative or whatever. Can I join in on the fun? And in this type of context, the sky's the limit. Because just as I have an interaction over here on the left, I can have another interaction over here on the right. The molecules are not bonded to one another. I am not saying this is Cl to H to Cl to H with an H down here and a Cl down here. No, these are not formal bonds. They are an attraction between the molecules that help us understand how they're oriented and packed. Joel, I see your hand. What's the question? What's the intramolecular force? Oh, thank you for catching that. Intermolecular force. Thank you for catching that. So it's important to understand the difference between the two forces. Intra is that which is already found within a molecule after they've bonded together. Inter is what connects it to other molecules. Now, one of the biggest known examples of an intermolecular force is what's known as hydrogen bonding. You see, hydrogen is the smallest atom. It only has one electron. That means no matter what, if you have a molecule, the hydrogen is going to be slightly positive. This leads to some really cool phenomena. If we have a water molecule as such, we know, of course, that the hydrogens are slightly positive and the oxygen is slightly negative. What will then happen is that these molecules will then be attracted to another water molecule, where the slightly positive hydrogen gets attracted to the slightly negative oxygen. And does it just stop there? Not at all. Guess what's going to happen? Another water molecule is going to come in and be attracted to the hydrogens. And for lack of a better phrase, we can keep going. Because these forces are not bonds, but merely attraction, no octet rule is broken. Instead, what we form is a network of loosely attached molecules. And for such a small molecule, H2O, the sky's the limit in terms of how big this network can become. In fact, hydrogen bonding is the phenomena that explains water's high boiling point. You see, to a lot of people, when they were first studying water, water has always been known for its stability, for its utility. One of the things that chemists couldn't quite rationalize is how could a molecule of just 3 atoms have 100-degree boiling point? That's a really, really high temperature. Here it is. It's because through the polarity, through hydrogen bonding, it's not just 3 atoms. It's a network of all of these molecules. We're talking an infinite amount of hydrogens, an infinite amount of oxygens, all connected together through these attractive forces. So when I heat up water, I'm thinking, okay, I got to boil this. I got to break every single one of these network connections. And that's why the boiling point of water is so high. Because you're not just breaking a single water molecule, you're breaking that infinite network. hydrogen bonding is one of the most common types of forces seen. And as you can tell by the title, hydrogen bonding involves the loose attraction between hydrogen atoms and electron-rich atoms. For example, if I were to come up with another molecule, let's say HF, well, guess what's going to happen? That HF, that hydrogen, will be loosely attracted to the nearby fluorines. And this is just a small snapshot of the network. Now, these forces, these attractive forces that exist between molecules, are not just useful for our understanding of chemicals, but they help us understand the world. Has anyone ever seen a gecko run across water? Maybe you've seen one of those like TikTok or Instagram reels of the gecko, the way how it's running. It's kind of like skating on the surface of the water. It's not touching. It's just each paw is just like it's ice skating. The gecko doesn't run, right? It skates above water. How does it skate on water without dropping? These forces. The webbed feet of the gecko has these types of molecules with hydrogen bonding and allows it to be attracted to the water, such that just like an ice skater, the gecko skates over the surface of water. It's because of these attractions. So understanding inter and intramolecular forces has implications not just in the chemistry world, but even in places like zoology. Because understanding hydrogen bonding is what helped zoologists understand, oh, that's how the geckos are able to run across water without dropping or drowning. They skate because their webbed feet are literally attracted to water. And that attraction is what keeps them skating. There is another implication. There is what is known as an induced dipole. Now, it should be clear by now that not every molecule will have a polar moment or a dipole. The most common examples we've seen so far, of course, HCl. And one of the ones that we saw that was nonpolar was F2. Where, in the case of HCl, we can draw the polar arrow that clearly tells us slightly positive and negative. And of course, in the case of F2, this is nonpolar. Why? Because there is no uneven sharing. They're both fluorines, they're equally sharing. Well, let's say you go in the lab and you say, hey, can I just add these two together in a beaker, a flask? Can I just combine them? Hell, why not? And you say, okay. I put these together. And in our flask, we have these molecules that will eventually hit upon one another. We know already that there is a dipole on the hydrogen and the Cl. But guess what happens as a result of that dipole? It induces a dipole moment onto the fluorine atom. You see, that hydrogen is so darn positive, or rather slightly positive, that it says, well, I want to be attracted to something. I like being attracted to negatives. So tell you what, fluorine, why don't you take on some of the electrons and let's you and me hit the town together? Fluorine says, but what about the fluorine I came with? What about that? Well, don't worry. Because by inducing this fluorine to be negative, you are now creating that uneven sharing such that the other fluorine becomes positive. As a result, we are now able to draw a dipole moment for a molecule that we know to be nonpolar. In the case of an induced dipole, a polar molecule literally induces a dipole in a non-polar molecule. Do we have any questions so far? Yes, Joel. Yes, but when we say electron rich, we sometimes just mean richer than hydrogen. But you are correct. Anions are absolutely, objectively electron rich. Yes. Okay. The last thing we'll talk about under this topic is dispersion forces. Nonpolar molecules can spontaneously develop polar moments or develop polarity. Now, how does that make sense? I've literally just been telling you that if there is no uneven sharing, then there is no polarity. So how can they all of a sudden they just out of nowhere spontaneously develop it? Think back to our tug of war analogy. We talk a lot about how these electrons are distributed between the two atoms. Overall, the net effect is that it's even on both sides. But just like a game of tug of war, it's kind of in dynamic equilibrium. In other words, at an instant, polarity can be established. Just randomly. We're talking about a time scale of like milliseconds. At an instant, polarity can be established because in the game of tug of war, sometimes the left will win, sometimes the right will win, but the net effect in a nonpolar is that it's overall neutral. But at an instant, polarity can be established. This is what allows nonpolar molecules to loosely attract other nonpolar molecules. Now, the fact that dispersion is kind of all based on this idea of spontaneously developing polarity. I mean, you don't influence it, you don't trigger it, it just spontaneously develops polarity. is what also tells us every molecule exhibits dispersion forces. Because if every molecule can just spontaneously develop polarity, then every molecule exhibits dispersion forces. These dispersion forces are what explain the stability of a wide range of molecules. It explains why some molecules have a higher or lower boiling point than water, because the extent of the dispersion forces will differ. Do we have any questions on inter or intramolecular forces? Yes, Elena.
That are designated to polarity, because you said it's like a tug of war sometimes, so I'm assuming there's like an average amount for the deadbolt.
Are you asking if there is a number assigned to the charge that's slightly, or to the strength of how much they pull?
Like, is there a numerical amount of polarity?
There is a numerical amount. As far as the individual strength, that actually comes back. Let me go back here. All the way back in module 1. Where is it? Electron affinity. If you recall from module 1, electron affinity is how much atoms love electrons. Electron affinity, or rather its trends, right, is what tells us the strength of individual atoms. As for the overall net number, that just depends on the molecule at hand. That's nothing you can necessarily predict without knowing exactly what molecules are involved. Okay. All right, with that, we'll end lecture for today. We do have a wet lab based on thermochemistry. Please come dressed appropriately. I'll see you guys in about 15 minutes. If you came late and I have your exam, come to me now so I can hand it back to you.